This video is about moderators. It emphasizes the statistical aspects of the analysis rather than the software. There is a video on the software metaphor for moderators that emphasizes the how you do it. But this one I'm going to talk more about what it means, and the background, and so forth. So a moderator is a third variable that conditions the relations between two other variables. So for example, if we're interested in the SAT quantitative scores and math grades in college, we can predict grades in college from SAT scores. And if we do that in a school, we typically will find that the correlation for females is greater than the correlation for males. So sex would be considered to be a moderator. Usually in meta-analysis, the effect size is a relation between an independent variable and a dependent variable. So any variable that we have in our data analysis that we use to predict the size of that is a third variable that conditions the relations between the two, and that's why we're calling them moderators. We can think of two basic types of moderators. First is the categorical or nominal type, and this is analogous to factors in analysis of variance when we're doing primary research. So sex, race, study type, so if we want to look at published versus unpublished manuscripts, or dissertations versus non-dissertations, or something like that, we would analyze by an analog to analysis of variance for meta-analysis. And if our independent variables are continuous, like the time between test and retest, or the average age of the participants, or the number of visits, or the duration of therapy, or something like that, we would use a weighted regression, sometimes called meta-regression, to analyze the data. So just as in the analysis of the effect sizes, we can talk about a fixed or common effects model, and instead of a random effects, it's customary to talk about a mixed model when we're going to include moderators in the model. So in the fixed or common effects model, the moderators are expected to account for all the systematic variance in the effect sizes. So you're going to have variability that's due to sampling error. And the random effects variance is the variance above and beyond that. If the moderators account for all of that, then you're back to a fixed effects because there's no more random effects variance after you include the moderator. So that's kind of convenient. In the mixed model, the moderators account for some of the variance, but not all of it. So there's some random effects variance left over. So you can then recalculate the weights using the residual random effects variance, and then you can re-estimate conditional means and so forth. So turns out there's more than one way to consider the error and the weights when you're going to recalculate things, including the random effects variance. Metafor only uses the pooled error. So it's going to have one error variance that it will use. CMA gives you the choice of either pooled or separate. Okay. In theory, meta-analysis can contain both continuous and categorical variables at once, and it can contain an unlimited number of independent variables, just like you could for regression. But in practice, most people wind up doing one independent variable at a time, and often there are only a few of them. The reason is we typically don't have very many studies. So in a primary study, you have hundreds of observations, and so you've got 250 people. You can put 2 or 3 independent variables in that equation and not worry too much about it. But in meta-analysis, you might have 30 studies, and now you put 2 or 3 moderators in there. All of a sudden, you got a problem. Typically, there will be missing data. So, each of the primary studies won't have all the information you need for the moderator, only some of them. So what happens is when you try and run a model that has all of them in it, you basically have no observations left. And so that's why people usually just run it one independent variable or one moderator at a time. There's problems when you only have a few studies. Of course, there's problems with type 2 errors. You don't have much power. With 40 observations in regression, you got to have a pretty big impact from your independent variable to detect it. And so that gives you type 2 error problems. Type 1 error problems happen because people doing a meta-analysis oftentimes want to be thorough. You don't want to do this quantitative review more than once, and so you code everything you can think of, and now you have 40 studies and 400 independent variables, and some of those are going to come out significant. So that's your type 1 error. So this is the nature of what we're doing here. There isn't any escaping both type 1 and type 2 errors. So when you're reading your results of the meta-analyses, you have to take these with a grain of salt. And that's one of the reasons why I say to people, don't analyze moderators unless you hypothesize them up front. And that's why you should be looking for the hypothesized business in the introduction. Okay, so now suppose that this is hypothetical data, but suppose we're looking at the correlation of SAT and grades for males and for females. In this case, we just have males in the first 3 studies, and we just have females in the second 3 studies. That probably wouldn't be the case in a real set of studies, but the effect sizes shown here and their confidence intervals are indicated by the wings, and the heavier studies have a larger symbol for the effect size, and the wings tend to be smaller. Here's our random effects estimate, and it's got this value of 58 is our overall mean, and the confidence interval for that is 46 to 69. All right, so now I'm going to walk you through the computations of this, and this is what metafor will do if you ask for Dersimonian and Laird. So here we've got the correlations between the SAT and the grades. Here we've got the R to Z transformation. We've got the sample size for each of the studies. The weights are the inverse variance weight. So we're going to R to Z, and variance is 1 over n minus 3. So the weight is the inverse of that, n minus 3. These are the categorical labels for the moderator. Okay, so we want to know, go back here, we want to know what's the correlation overall, and is it different for males and females? So is there a significant difference here? All right, to find the overall result, we take Z times W, and so here we've got Z times W. And if we take the sum of W times Z divided by the sum of W, so here's the sum of W, here's the sum of W times Z, that gives us a weighted mean, and that's 0.58. Okay, so if we now subtract 0.58 from 0.42 and square that and multiply it by the weight, we get 4.9. We add those things up, we get 21.99. So that's our value of Q, our weighted sum of squares. And Q is related to chi-square. So if these are homogeneous in the population, then this thing will be distributed as chi-square with k minus 1 degrees of freedom. So we've got 6 studies, so that would be chi-square with 5 degrees of freedom. And 21.99 is much bigger than we would expect with 5 degrees of freedom. So we'd expect to see a sum of squares, sum of squares about 5 here. All right, so our random effects variance component is estimated to be 21.99 minus 5 over this normalizing equation here. So our estimated random effects variance is 0.16. Let's continue with the example. Our male studies give us these data, and we've got a weighted mean of 0.45, a weighted sum of squares of 0.421, and we've got 2 degrees of freedom 0.421 is less than 2 degrees of freedom, so that's not going to be significant. Here we're going to take 0.421 and subtract 2, and that's going to give us a negative number. So by convention, when we have a negative variance estimate, we set it to 0. For the females, we've got these values of Z and these values of W. When we compute the weighted average, we get 698. We get a weighted sum of squares of 2.58, which is also non-significant with 2 degrees of freedom. Our estimate for the random effects variance is 001 for these folks. Okay, so now what we want to know is the effect size for the males the same as the effect size for the females? Is there a difference in the effect size by sex? Is the SAT more correlated with grades for one sex than for the other? Well, here we've got the total we found was 0.58. For the males, the average was 0.45. For the females, it was 0.70. The total Q was 21.99, and for males, it's 0.42. For females, it's 2.58. All right, so it turns out that just like an analysis of variance, where you've got the total sum of squares is equal to the sum of squares between plus the sum of squares within, you got the value of Q, weighted sum of squares, is equal to between plus within. So these are sums of weighted squared deviations. So 21.99 is what we had for the total. Well, we know what we got for within. That is 0.42 plus 2.58, and that gives us a whopping value of 3. So our between is what we get when we take the total and subtract the within. So we got 21.99. We subtract the 3, we're left with 18.99, and that's a nice big value with 1 degree of freedom. So when we test the moderator, the moderator significance test is the test of this between Q. It has degrees of freedom, that's the number of groups minus 1. So here we have male and female, that's 2 groups, so our degrees of freedom are 1, and our Q between is 18.99, so we got that chi-square test going, and that's a significant result. So we would say that these means are significantly different. Here with 1 degree of freedom, if we had a moderator that had multiple categories, so let's say we had 3 different kinds of therapy, and we're looking to see whether the different kinds of therapy were equally effective, then we would have, we would add 3 different withins and subtract them from the total, and then we'd have 2 degrees of freedom here. All right, so we've got the group means. We got in Z, we've got 45 and 70. We've got these confidence intervals. When we take the inverse of the R to Z, we go from Z back to R, so that's that tan H function. We get 0.43 and 0.60, and these confidence intervals come from translating these things back into R from Z. Same for the total. Okay, now in the previous example, the moderators accounted for all the variance in the effect sizes except for sampling error. But suppose that they didn't. Suppose that the Q within is 6, and we had some random effects variance left over. So it's 001878. And now we could re-estimate the means using that. So we could come back and have that W star instead of the W, whereas the W star is 1 over the sampling variance plus the random effects variance. All right, so what do we got here? All right, here we've got the random effects variance is 0.178, and the weights 1 over the first one plus random effects variance. So if we do that, What do we got here? Here's our weights. So our initial weight was 197. Now it's 143, 172 to 130. So notice that these are smaller and they're more similar to each other. So the bigger the random effects variance gets, the smaller these weights become and the more they are similar to unit weights. So here we get a mean of 0.58, and so it really is not much different than what we had before. Whether you get a difference or not really depends on how discrepant the big samples are. So if you got some really discrepant big samples, then the revised mean, when you use these, will change a lot. But if they're all pretty much the same, then it won't make much difference. Our sample sizes are all pretty similar. So you need to have a big difference between these things. You need some big and some small samples, and they need to have some relation between them. Okay, analog to ANOVA. Review the Excel and R analog to ANOVA programs. Okay, so here's where you go and look at the video on the moderators and see what it says. You should avoid interpreting Q-tests from the random effects model if the RAVC weights were applied. So don't look at the significance of the Q-tests for the places where the weights were applied. So the Q values, they're only good when you have fixed weights. So if you're going to do the test yourself, you want to use the fixed effects. But you don't really have to worry about that too much because metafor is going to do the work for you and it'll give you the right results. Okay, so here we've got the input file. So I've got Z and W is n minus 3, and here's V, so that's 1 over n minus 3, and I've got the coding for sex, 1 for males, 2 for females. Okay, you have to remember that when you're looking at your output, otherwise you will be mystified as to what it means. All right, so here I have metafor run, and it says SAT results gets RMA, so that's metafor. Y sub I equals Z, so here's my effect size. V sub I equals V, here's my variance. So I've got Z as my effect size, V is my variance, and those are the things that metafor needs to know. Method is DL, so I'm going to ask it for that Dersimonian and Laird estimator of the random effects, and when I write it in data, I called it data 1. And then I ask it for the output, and it says random effects model K is 6, so I had 6 studies, and it tells me my estimator was Dersimonian and Laird like I asked for. It gives me estimated heterogeneity is 0.2, tau is 13, I squared is 78. So it's you could say there's plenty of variability here. Test for heterogeneity, we've got 5 degrees of freedom for Q. So I got 21.99, so there's a difference in rounding. P-value is quite small. Test for heterogeneity, that's what this is, the Q test, it's significant. Okay, so here's my model result. The overall estimate is 0.58, which is basically what I got. Standard error is 0.6, Z is close to 10, so P is very, very small. Confidence interval goes from about 4.6 to about 6.9. Okay, so that is the results from running metafor on the all 6 at once. And we're getting results that look like what I got when I did it in Excel. Now we're going to do the moderator test. Okay, so let's look at how that works. Y is Z, B is V, mods equal, and here I've got that tilde, so in my keyboard that's on the upper left, squiggle, tilde, factor, so when I read the data in, it looked like this, and so R has got this as an integer, and I need it to be not an integer, but rather a factor. If I just put sex here and I don't tell it's a factor, then it's going to think it's a continuous variable. So I have to put factor sex, and that tells the computer that this is a categorical variable. All right, and then so I tell it to run, and it comes back and says it ran. Oops. So sex is fixed. The study is random. I've asked it for. I didn't tell it what I wanted to do for the random effects, and by default it does restricted maximum likelihood, which is what Fichtbauer likes, and I do too. Estimated amount of residual heterogeneity is 0, so it's telling you that it thinks once you introduce the moderator, that accounts for all that random effects variance. Here's tau is estimated to be 0, I squared, I love it, estimated to be 0, test for residual heterogeneity is not significant. I'm not sure that I want to pay attention to that. I think I might not. But never mind that for now. Okay, so what we want to know is, here's the test for the moderator. Okay, so it says coefficients 2. So this thing is the thing coded to, not 2 variables. So tested this. All right, so what do you get? You get the model results estimate, where it says intercept. That is the value of the mean for the males. And factor 2, that is the difference between the males and the females. Okay, so this thing right here is the test of the difference that the moderator makes. So it's being tested against 0, but it's not for the value that it has, but for the difference between the males and the females. So if you want to know the significance of the moderator, that's the difference between the two. That's right here. Okay, and notice the way I did that. I said factor sex, and that's what you get when you do that. All right. So the second estimate is the difference between the males and females in the mean effect size. All right. Now I'm going to do the same thing, except for I've got mods factor sex -1. So -1 means suppress the intercept. All right, so I'm going to get the same results all the way through, except now that I'm down here, I've suppressed the intercept, and so I've got, it says factor sex 1, factor sex 2. So here's for the males, here's for the females, and we get 45 and 70. And p-values are, very small. So this one is a test of whether the male mean is 0, and this is a test of whether the female mean is 0. And you can see that they're not. But this doesn't tell you whether these two things are different. It just tells you whether they're not 0. Whereas this one, the previous one, this one says, okay, is that 0? And go no. And then this one is the difference between males and females 0? And you can go no. So if you want to see what the actual estimates are, then you need this. If you want to see that whether they're significantly different, then you need to do it like this. So that's an important distinction, and easy to forget. All right. So test of moderators, 1, 2, 3. So this is a test of the simultaneous effects. All right, that's a joint test of whether both of these are 0. So you can have some of these be 0 and some not, and this may or may not be significant. In this case, they're both significant. The whole model is significant. So this is kind of like the test for R² for the model in regression, whereas this would be the test for the individual B weights in regression. And the idea is to import the data and run the model. So is the educational treatment, is that helpful in getting people done, getting them out of the hospital, and does it the size of that vary by journal versus dissertation? All right, I'm going to let you try that. Go to Canvas to get this data.